5, 4, 3, 2, 1.
Life could be a dream, life could be a dream. Shoo-doo-doo-doo, shaboom.
Life could be a dream if I could take you up to paradise up above, and you would tell me I'm the only one.
Hey guys, this is Adam Prince. Welcome to my YouTube channel. Today we are going to talk about some advanced NLP concepts. First, let us talk about sequence to sequence model with attention, and finally transformer models. First, let us see about sequence to sequence models, shall we?
Now, let us see about sequence to sequence network. So, as we know, a sequence to sequence network, that is seek to seek, or the encoder decoder, it is a case where the length of the input sequence does not have the same length as output data. So, let us take an example of translation of English sentences to French. So, as we see in this diagram, that is, he loved to eat tourism zu and we see the architecture of it, that is embedded and gives us softmax. So, let us focus on the encoder. The encoder simply takes the input data and trains on it, then passes the last state of its recurrent layer as an initial state to the first recurrent layer of the decoder part. We see the input that is getting as an English sentence, and with the initial state, it depends on the initializer we use, as we see it's in the UI or something else. So decoder. The decoder is exactly the opposite. It takes the last state of encoder's last recurrent layer and uses it as an initial state to its first recurrent layer. The input of the decoder is the sequences that we want to get. That's our output. That is in this case our French sentence. So as you see, the decoder input is a French sentence, and finally you get as the encoder's last recurrent layer. So you see a generative model chatbot of like the question is like, are you free tomorrow? Yes, what's up? So this is like basically this is used in like in the translation like Google Translate or translator apps like chatbots, and also like if you want to like self chatbots like as you see in this group in this chatbot, you ask a question and it replies according to it. So I have included a program in it which I got from the GitHub. Like it imports some strings and pandas, and we build concepts of complex models. So basically, as you observe in the program, it has an input layer which takes the English sentence and passes it to the embedding layer. The embedding layer takes the English sentence and converts each word to a fixed size vector. And there is also an LSTM which has two layers, where the first LSTM takes a vector and that represents a word and passes it to the next layer. So we see the words of Q, D, DNN, LSTM layer instead of LSTM because it's much faster. And in the second layer, we do the same thing of the previous layer, but instead of passing it the output, we just state it as the first LSTM of the decoder. And as you see, the encoder's architecture, it's a very vast architecture. So I also included the program of the decoder. So the decoder is made up of an input layer, which as simple as that I said in the previous one. It takes the French sentence and passes it to the embedding layer. And in the embedding layer, the took French sentence is converted to each word to a fixed size vector, and next it passes to the LSTM vector. So every time the step is taken, a vector that represents a word is passed as an output to the next layer. But in this decoder, we initialize the state of this layer to be the last layer of the last LSTM from the decoder. So what does this second LSTM do, as I stated in the next point? It processes the output of the previous layer and passes its output to the dense layer. So what is the dense layer? It is also known as the output layer. It takes the output from the previous layer and outputs a one hot vector representing the target French word. So basically there is also a fault here. That's why we approach for the transformer model. So you see each and every English word, when you convert it to the French of the French, which is in colloquial terms, if for an example, if it contains like 4 English words, it may give like 3 English words. So there is not a separate algorithm, like for this amount of English words we will get this amount of French words. So if the longest English sentence is 10 words, we have to take 10 time steps to get its French translation. So each has its error. So this is how it is. So we also use an optimizer, that is RMS prop as stated in the code. This optimization is good for the recurrent neural networks, and we use categorical cross entropy as the loss function because we treat each word as a category.
You're right. That was sounding difficult. Now let us see about the transformer models. Well, when I remember it, I remember this one.
So let us break into another thing. Inside the encoder and the decoder, that is the neural networks with self attentions. So what are the self attentions we have? So basically, we just noted the sublayer needs to be same that I mentioned, and according to the powers of the six sublayers, we get 5 and 2 dimensions of Zi and Vi. So additionally, we allow the model to focus on different positions by calculating the self attention multiple times with the differences of the Q, K, and V vectors, and we take an average of all these outputs to get our final Z. So we have three vectors of we take these three vectors and reduce the size by the method of matrices, and we measure every sets, that is of the matrices of the hidden sets, as I mentioned in the previous point of the attention. It is grouped into a matrices of repeated attention heads into a multi-headed attention, and lastly averaging to get the final Z, we concatenate it. So this is the multi-head attention. So the third one, we see the input and output piece processing. Here after things are easy. So the input words are represented in the form of embedding. As we already know, this is done for both the encoder and the decoder. Word embedding on their own lack any positional information, which is achieved in RNN by the process of the sequential nature. Meanwhile, in self attention, due to softmax, any such positional information is lost. So, preserve this positional information, the transformer injects a vector individual input embeddings, which could be used as a word embedding or corresponding for the words. These vectors follow a specific periodic function, which is, for an example, you can take it as a combination of various sines or cosines having different frequency, but specifically not in sync with each other. This model learns and is also able to produce and determine the position of individual word with each other, which is solved by the previous model. So this injected vector problem is called as the positional encoding, and it is added to the input embeddings at the bottom of the encoder and the decoder. So finally, we get to the bottom one, that is the decoder stack. The output of the decoder stack at each step is fed back to the decoder. So it is pretty similar to the steps taken in the RNNs which we used in the hidden states in the previous one. So just as we did with the encoder inputs, we embed and add positional encoding to these decoder inputs to preserve position of each word. This positional encoding plus word embedding is a combo which is, as previously mentioned, the masked multi-headed self-attention. So this self-attention sublayer in the decoder stack is modified to prevent these positions from attending to subsequent positions. So basically you can't look at future words. This masking ensures that the predictions for position I can depend only on the outputs at positions less than I. So this total is called as the encoder decoder attention, which is seen in the green layer of the diagram. It helps the decoder focus on the contextually relevant parts in the input sequence, not noticing the other vectors. So this part is basically similar to the global attention vectors. The Q vector comes from the output self attention layer. So we do the softmax again to select the final probability, which gives you a good precision of the precision of the words and gives a good probability. So, concluding, we understand what a self attention is, how to calculate self attention from these VKQ vectors. Multi headed attention is an efficient modification of self attention that uses smaller sets of V, K, and Q again and concatenates the output to finally get the output of Z. Then we saw how the three kinds of self attention are used in the module and followed by the pre processing done on the inputs for the encoder and decoder.
Hey guys, thank you for taking your time and reaching out to my channel. And also make sure you could subscribe, like, and also click on the ring bell button. Thank you. And Ms. Premalata ma'am, please stay on for the next 5 minutes.
All right, now let us talk about the custom NER using Spacey. So what do we do here? So basically we do a tokenization which is a part of POS stacking with lemmatization of the features and with NER, the name entity recognition, similarity and with text classification. So what is an NER? An NER is a name entity recognition with a subtask of information extraction, which is helpful to locate and extract the entities mentioned in the structures, like quantities, monetary expressions, and many things. So these are the so we have planned to extract some codes with basically like with the person, gp, date, money to extract and to find what is what and what is the right. So why are we constructing in custom str? So the spacey, that is the which are planned to do it, in simple words, we trained our model with created object and to how to say it, like extracting information on it. So this is like a test case model on how to work on it and how to do it, and we do it with a space pipeline, and also we do it with an anatomy of our trained data with the first index consisting of name, degree, designation, and companies worked at, and with the second index of entities that we are hooked upon. So that's the conclusion. So as we have created training and add a custom NER to train our model.